Okay, folks. Let's see. So today, our plan is to discuss Wkb approximation, and this stands for three names: Wendell or Wenzel. Nobody remembers these guys' names. Wenzel, Kramers, and Brillouin. Actually, they're famous for other stuff too, these guys. These were three smart dudes. Okay, so Wkb approximation. And so this is a new topic. And it's a new approximation method. And I started to introduce it at the last lecture, but I'll just kind of introduce it again right now. The idea is that we've already been discussing two approximation techniques, which is perturbation theory. And this is, we found, is pretty useful when you can write your Hamiltonian. I mean, the whole point, first I just want to say the whole point is we want to solve the Schrodinger equation, okay? That's the whole point, is to solve that equation. And the only question is how to do it. And so for perturbation theory, we see that if we can write the Hamiltonian as a known Hamiltonian plus a small perturbation, then it's useful. Then we use perturbation theory and all the tricks of perturbation theory that we've discussed. On the other hand, we also learned the variational method. And the variational method did not care the size of the Hamiltonian or perturbation. The variational method was simply a very clever trick for basically finding the ground state. It's good for getting the ground state. And you can get a limit. The variational principal limit is always greater than or equal to the actual ground state. So it's upper limit on the ground state energy. Okay, so that's good. But now we're going to do a new one, which is called Wkb, named after those three guys. And this is useful for when we have big energy, or in other words, short wavelength. And the idea is that the potential is slowly varying. And then it works pretty good. In other words, if I have a potential that looks like this, that's my v of x, and if my wave function is here, see, there's my wave function. So you can see a slowly varying potential with very short wavelengths of my wave function. So then Wk is good. Wkb is good. Okay, and so so today I'm going to go through Wkb, and I just want to say that, you know, the utility of these approximation methods, I sort of did them in priority of this class. You know, the perturbation theory is the most important one. Then variational principle is pretty important and quite useful. And I would put this Wkb, like, you know, in third place. I think it's not as useful as the other ones, but it's still quite useful, and it pops up a lot. And and it gives you a useful way of thinking about the Schrodinger equation. So it's really worth thinking about and going through. And so there's different ways to derive it. There's like a fancy mathematical way, and we're going to do that. But before doing the fancy mathematical way, let's just think about it intuitively, because the idea of the Wkb approximation is very simple. Very simple, simple. And so I want you to understand the simple thing, and then we'll do you can always derive it using complex mathematics. But let's try to understand it in the simple way. Simple way. And so the thing to remember is that let's consider a constant potential. a constant potential. Then we have this, like a square well. Square well. All right, and where that's minus V naught. And so then you see if I have so then you see that if I have some energy here, E, for the particle, then you guys know how to get the wave function. You guys sort of know what to do. You guys know that you've done this problem before, and so you know that to solve H psi equals E psi, then you guys know that H is equal to negative H bar squared over 2m d squared dx squared plus p of x psi. Oops, sorry, shouldn't have done that. And then you can say H psi, well, times psi is equal to, I just want to not write so much. Okay, so that's the problem. That's what you got to solve. And so you guys know that for if V is a constant, then this becomes really easy because it's negative H bar squared over 2m d squared dx squared. Then you're going to have this V, let's see, we'll do that plus V minus V. Let's see, what's the best way to solve this? Plus V, well, I don't know, let's, plus V psi equals E psi. And you guys have all done this before, and you know that then you can write, you know that if psi is equal to E to the ikx, a wave, a plane wave, then you plug that in, and then you get, you end up with E is equal to H bar squared K squared over 2m plus V. And so then you know that you get your famous K is equal to square root of 2m E minus V over H bar. All right, so so you've all done this before, right? And so then you know that if so that means that if you see that if the well is deeper, so deeper well, then what does K do? So if the well is deeper, then what happens to K, your wave vector?
Increases.
That's right, because V is a negative number and it's minus a negative number, so K increases, so K is bigger. And if K is bigger, what happens to your wavelength? Bigger K means what happens to the wavelength? Right, smaller wavelength, lambda smaller. Okay, this is intuition that you got last semester or even earlier in Physics 7C. Okay, and so you just kind of know that for these square wells, then the solution of the Schrodinger equation is this very simple plane wave. But now what I want you to do is to think about that solution a little differently, because here, so we can see then that inside of this square well, we have this solution which goes as psi E equals E to the I kx, right? Now, what you would normally do to solve this correctly, and you did do this last semester, is you would match everything at the boundary conditions and you would look at all the different possible solutions and match them very carefully at the boundary conditions, you know, right? That's what you did. But let's just but let's not go through all that bother. Let's just notice that this function, let's not worry about the boundary conditions so much, but let's just notice that that function solves the differential equation. And let's take a closer look at this function, e to the I kx. And let's notice that that's the same as e to the I phi of x, where phi of x is a phase. And obviously phi of x in this case is equal to kx, right? E to the I kx. But phi of x, I can think of it like this. It's an integral from 0 to x of k dx prime. And why did I do that? I want you to think about the solution of the wave function a little differently now. Rather than just coming up with these functions that whatever function like Bessel function or whatever, or plane wave, rather than coming up with this function, I want you to think about it in terms of a phase. And so I want you to think that the solution, to get the solution, then if we start with some phi, a known phi, like if we know the phase at, say, here, 0, at some starting point, x equals 0, then to get the wave function at some further x, then to get psi e of x, then you just have to wind the phase, which means psi e of x is equal to e to the I 0 x prime. Oops, missed that. 0x k dx prime, where this is the phase. And so I'm just taking a very simple solution and I'm sort of making it more complicated. You know, I'm like sort of recasting it in like a different language. But this different language is very useful. And so the way to think about it is that there's a little wheel. Like let's just, no, that was actually not useful. Let's not do it like that. Let's do it like here. Let's think about, there's a little wheel that's rolling. It's a little wheel. And that wheel gives the phase. And so think of the wheel as literally rolling in space. The wheel rolls in space. And so the phase of the wheel, is this. The phase of the wheel, you know, because the wheel is literally rolling. And so this is, you know, an arrow that goes to the circumference of the wheel. This angle is phi. And so then I can see then that phi, if the wheel is rolling, then the phase is equal to the circumference, or it's like the distance it's rolled, divided by, can you guess? Divided by what? A wheel is rolling. It's actually a very simple geometrical question. It rolls some distance, x, some distance, and what's the phase? What is the phase change of the wheel if I just sort of pick one point on the wheel and say, I'm following the angular change of that speck on the wheel? The phase is distance divided by what?
Is it circumference?
Close. No, the distance is like the circumference, okay?
2 pi.
No, that's yeah. You're good. You know, you're dancing around. It's like circumference is equal to 2 pi radius. That's correct. But no, that's not what I'm talking about. I'm talking about the angle. The phase is the angle. What's the definition of an angle? You know, you have the arc length. That's the distance. Angle equals arc length divided by what?
Radius.
Yeah, that's the definition of angle. It's distance, which here is arc length, divided by radius. So you guys all know that. I know that you all know that. And so that's equal to x over r. But here the thing is, let's think of the radius of the wheel is equal to 1 over k. k, 1 over k. And so that means that phi is equal to, if the radius is 1 over k equals r, then 1 over r equals k. That's kx. All right, so I just want you to see that. So the radius of the wheel is 1 over k. And so if that little wheel is rolling, then the angular evolution of that wheel literally gives you the phase. All right, that's just another way of recasting the solution you already know. And so the little rolling wheel gives phase. Okay, and the wave function psi e of x is equal to it's going to be e to the I, your starting point 0 to x k dx prime is equal to e to the I kx. You see that, okay? Just another way of writing it, and the phase, the distance. This phase is the integral from 0 to x of k dx prime. Okay, so I hope that you can kind of see that. And so now, if I let's do a more complicated case. So now you can see that if I have, using this kind of idea, if I have a weird potential like this, and now if I put my energy here, and this is my, let's just say that this is my potential, right? And this is x, and I'll call this x1, and this I'll call x2. Let's see, I'll call this v1, I'll call this v2. Then you can see that when using the same reasoning, then I'm going to get some, if I look at if I have this energy, then in this region, I'll call this region region 1, and I'll call this region region 2. Then in region 1, what's k? K is equal to what? Tell me.
Square root 2 times e minus v1.
Right, except v1 is negative because it's down below.
Oh, plus v1.
Yeah, so we'll call it plus v1. Or we'll do it like that, over h bar. That's good, yeah. And so that means that in this region 1, the wave function has some wavelength, yeah? And that phase, and so if I start here with some phi at 0, then I can see that in this region, if I try to understand my wave function, by this little wheel that's rolling, then I can see that it's e to the I integral from 0 to some x prime k, and that's k1 dx prime. So the little wheel is rolling, and that's going to be the phase in this region 1. I'll call that phi 1. But then, once the little wheel hits the second region, what happens in this region 2? What happens to, now I have k2 is equal to square root of 2m, and now it's going to be e plus v2 over h bar. And so what happens to the wavelength in region 2? What happens to the wavelength in region 2? Is it bigger or littler?
It gets longer.
Yeah, because is k bigger or smaller?
K is smaller.
That's right. I want you just to see that. That's right. And so now it gets longer, see? Like that. And so what happens to the size of the little wheel that's rolling? The wheel is rolling, rolling, rolling. But what happens to the wheel in this region, region 2? Is the wheel bigger or littler?
It gets bigger.
That's right. So now I have a bigger wheel rolling in region 2. And so then I'm going to have here phi of x is equal to integral x1 to x, wherever that is. This is k2 dx. So you see now I have a bigger, the wheel is bigger. And so then I can see that the psi of e at some x, let's say x is greater than x1, then the wheel rolls through region 1, and it's going to be e, it's going to be basically e to the I. The whole point is that it's the whole total phase at the point x, which is going to be e to the I, all the phase that we get from the first one, which is going to be phi of x1 plus the delta phi from x2 to x1 to from x2 to x2 from x1. So so what you can see then is just going to be e to the I k1 x1. Shoot, I keep screwing this up. E to the I k1 x1 plus k2 x minus x1. Shoot, let me erase that. X minus x1. Yeah. Okay. So I want you to get that concept of like that rolling phase. And so this is the total phase. Total phase accumulated by rolling wheel. But the radius of the wheel changed from different locations because the radius of the wheel equals 1 over k, but k is square root of 2me minus v over h bar. So if the potential changes, then the radius of that little wheel changes. Okay, and so the main point that really drumming into the ground is that the function. So now what we can do, let's do a harder problem. Let's consider this. Here's a square well, which you guys have all done. And now I'm giving you a harder problem. I'm saying, what is the wave function if I have my energies here, and this is my potential, v of x. But now for my potential, I'm going to do this. I'm going to say, what happens if my potential does this? Now I'm giving you this really weird potential, okay? So now this is my potential. This weird, I put this weird bulge on the bottom. So it's this bizarre function that you've never seen before, just some weird function, v of x. And I'm asking you, what is the wave function, psi e of x? And all that I'm giving you is v of x. And suppose I'm saying that, yeah, and so then what would be your best guess as to the wave function? Can you guess a wave function? And I want you to think of this I want you to think that the wave function starts with some starting point, I'll call it psi of 0. But then the phase of the wave function evolves as because you can think of a little wheel is rolling from the starting point, and it rolls and rolls and rolls, but the radius of the wheel is fluctuating because the k is changing. And so what, well, here I'll give you a hint. The wave function at any point x inside of this well is going to be e to the I phi of x, where that is the accumulated phase of the wave function. And so I guess my question should be then to you, what is the accumulated phase? Because that is the wave function. Do you see how to think of it like that? So this is sort of like a different way for you to think about it, but it's a useful way to think about wave functions. So
we have to like integrate.
Okay, good.
Like k of x, which will be a function of v of x.
That's right. And we have to integrate over the x prime, right?
Yeah, up till x. Or
yes.
0 to x.
And now I'm asking you, what is this function k of x prime?
The root 2m times e minus v of x over h bar.
Yeah. You have just invented WKB. See, that's it. That's it. Because then I could just look at this thing, I could just say, hey, you give me this weird potential with some v of x, and you say, what's the wave function at some particular energy E? And I'll just say, well, I'll just wind my phase to that point. And it's just going to be e to the I integral from 0 to x, k of x prime, dx prime, where k, of course, is this thing, k of x prime. Yeah, that's it. So now, of course, that's really a gross approximation to the wave function. What are we missing when we do this? Can you guess what we're missing?
The amplitude of the wave function?
Well, yeah, but it's sort of like, that's right, but it's kind of like we're missing reflections, because what's happening is you have waves going in and then the waves are reflected. And so you're sort of missing the quantum interference. You're sort of oversimplifying the quantum interference. And when you really solve the differential equation correctly, what you're doing is you're really taking into account all of quantum interference. So I'll just say that this neglects some reflections and quantum interference. And that's why it's only an approximation to say that. Okay, so that is the concept of WKB. And so now what I want to do is let's actually derive it. So that was just all hand waving and talking about little wheels. But I think that it's useful to think about little wheels, because like we're going to do some equations, and the equations will make you feel better, because equations always make us feel better, make us feel more secure. But then in the long run, you will forget the equations. But maybe, if lucky, you will remember the little wheel, because that's how people are. Okay, so let's derive it. Let's derive WKB. And WKB, so here's the thing. So we're given some weird v of x, some weird potential, and somebody says, solve the Schrodinger equation. That's what they say to you. Solve it, damn it, solve it. All right, and you're like, oh, okay, how do I do it? And so you already have other techniques, that you've developed, but now I'm going to show you a new way to solve the Schrodinger equation. So the new way of solving it, the WKB way, is to do this. Let's assume that the wave function psi of x is equal to some function a of x multiplied by e to the I s of x, where this is some phase. S of x is a phase, okay? And this is completely general. So there's no approximation here. Because any function I could write in this way by the appropriate choice of A and S. Okay, so this is completely general. And so now let's plug this in, plug it into H psi equals E psi. Okay, where H is equal to our old friend, negative H bar squared over 2m, d squared, dx squared, plus v of x. Okay, so we plug this assumed solution into the wave function, into the Schrodinger equation. So we hit it, and then to calculate H psi, there's a little bit of algebra that I'm going to skip. And then after doing the algebra, this is what you get. You get this, and it's not hard. You guys go do the algebra on your own. D squared, because there's just some derivatives in there, right? It's just a little bit of work. You're going to get the second derivative of a of x plus 2I times partial derivative of a with respect to x times partial derivative of s with respect to x plus I times a of x times the second derivative of s of x with respect to x minus a of x times ds of x with respect to x squared plus k squared a of x equals 0, where k is defined as our old friend square root of 2me minus v of x over h bar. So that's a function of x. Okay, so k is a function of x. Okay, so this is just straightforward. I just plug this assumed solution into it. But now I notice that I have two parts. I notice that that it's a complex equation. I have a real part of my equation plus an imaginary part, I equals 0, right? In my differential equation up above, you can see it. So where's my imaginary parts? Like here's the imaginary part, right? I got a little I there. I got a little I there. And the real part is all the other stuff. Okay, so that's pretty easy to notice. And so what can I do now? I got a real part plus the imaginary part equals 0. What do I do next? Can you guess? We're doing math now. We want to solve this equation. What do you think I'm going to do? You've seen it before. To continue.
Set them separately to 0.
Yeah, exactly. Because if it's if it's a complex number that equals 0, then that means that the real part has to equal 0 and the imaginary part has to equal 0. So I'm going to set these both equal to 0. That's exactly right. And so that's going to give me two equations. And so those two equations are going to be as follows. I'm going to have equation 1. Then I get two equations. And equation 1 is going to be second derivative of a with respect to x minus a times second derivative of s, first derivative of s with respect to x squared plus k squared times a equals 0. All right, so I think you can see it's there. Okay, you see it. And then the second equation is going to be 2 times dA dx times ds dx plus a second derivative of s with respect to x equals 0. All right, and so now it turns out that the second equation can be solved, it turns out. And I'm not going to like figure out, I'm not, using some clever differential equation technique, it can be solved. And so let's not worry about how to solve it, but let's just look at the solution. You can just say, oh, I guessed the solution, and plug it in and see if it works. So you should see if it works. But this is the solution. The solution is a of x equals c over square root of ds dx. So this does solve that. This works. If I plug this into equation 2, it works. But notice I have 2 equations and 2 unknowns. So this just gives me one of the constraints, but I need another one, right? Because I basically, remember the whole point of this whole thing is that I got my wave function psi is a of x times e to the. So the whole point, I'll just rewrite it here. It's psi equals a of x times e to the I s of x. So we want that, and we want that. Okay, we want a and we want s. So we're trying to get them. So right now we have a constraint on a and s, but there's 2 unknowns, and so that's just one constraint. So I need the second constraint. So equation 1 is harder. And there's equation 1 up above. And it's harder, and so it's too hard. Equation 1 is too difficult because which is not unexpected because it's the Schrodinger equation. It's hard. And so we're going to make an approximation. And this is the whole crux of the matter. We're going to make an approximation, and this is the Wkb approximation. And that approximation is going to be that a of x is slowly varying, in which case the second derivative of a of x is equal to what? Tell me.
0?
Yeah, exactly. Good. You're getting the hang of it. Okay, so then that means that we're going to knock off. So this part of the equation gets knocked off. Okay, so now the equation is much easier. So now equation 1 becomes really simple because it's just going to be where did it go? It's up there. Yeah. Okay. So now it just becomes minus a of x ds dx squared plus k squared a of x equals 0. And now look at this. I can just cancel out the a of x. So simple. And it just becomes then it becomes ds dx squared is equal to k squared. Oh my God, so simple. And so then it just becomes ds dx is equal to plus or minus k. All right, so we got that. That's nice. We got ds dx, but then we also see, but remember k, k is a function, so k is square root of 2m minus v of x over h bar. It's a function. And so then we see that s of x is equal to what? What's s of x? Tell me, solve this equation. I'm underlining it right there. What's s of x? Solve that equation. How do you solve that equation?
It's the integral plus or minus the integral of k
Exactly.
dx.
That's exactly right. 0 to x, k of x prime. Oh, it's starting to look familiar, right? Remember? I was showing you before. So, so now we got it, because check it out. We up here, we have ds dx equals plus or minus k. So ds dx equals plus or minus k from below. And we can plug into there to get a. Actually, I don't think I want to write it there. It's going to confuse whoever's reading these notes. So so now we have it, because we have S star, and we have A star, and we see size is that. So let's put it all together. So so A of X, what did I say was here? Yeah, A of X equals C over square root of ds dx. So that means it's equal to C over square root of k of x, yeah. And then we have s of x there, and so now we see that psi is equal to a of x equals times e to the I s of x is equal to it's going to be equal to a constant over square root of k of x, that's a, but I can have two different signs of my s of x, so there's going to be 2 plus or minus I integral 0 to x k of x prime dx prime. Okay, and now because there's two solutions, a plus and a minus solution, that means each of them can get a different constant, c plus or c minus. And that is my WKB solution. Psi e of x WKB. That is the WKB solution. And so that's kind of the same thing we would get with the little wheel, right? We got the the little rolling wheel. So I just want you to see it's just basically it's just the accumulated phase. This is just accumulated phase. Okay, so but now by doing all that math, we got a little bit of extra stuff. We see that there's that factor of 1 over square root of k of x. So, doing the fancy math gave us a little bit more accurate thing. Okay, that is the WKB solution. And so now let's solve some problems. Now let's use it.
Can I ask a quick question?
Of course.
You know how you said slowly varying made a double prime of x 0? Can you kind of explain how you were able to know that was 0 using the slowly varying thing?
Well, yeah, it's kind of like, I mean, it's sort of like, it's like, I mean, here's the thing. It's sort of like, that if I have, let's see, if this is x, and if f of x is some slowly varying function, then the derivative well, I guess let's do it like this. Suppose, I mean, if f of x if f of x is some very slowly varying function like this, then you can see that the derivative is just barely changing because it's not varying very much. And if the derivative is barely changing, then that means that the second derivative is barely changing. That's basically the reasoning. It's not like super precise, but that's the idea. Does that make sense?
Yeah, I could roll with that, yeah.
I mean, there's other ways to think about it. I mean, there's a really nice derivation to describe the regime of validity of WKB, but I think I don't want to do that. I might do that. Do you come on Friday, or are you one of the people who don't come on Friday?
Yeah, I don't usually come.
Oh, okay. Because if you ask me on Friday, then there's another very nice derivation that shows the regime of validity in terms of energy and momentum and all this stuff, but it takes a little bit of time to go through it. I didn't want to do that today. So what I want to do today is I want to use it. I want to use the solution. Okay, so now let's use the WKB solution. And so there's two famous problems, two famous examples. One of them is bound states, and the other one is tunneling. And the tunneling one is even more famous. Get 3 stars, and this gets 2 stars. Okay, so applying WKB to find bound states and to do tunneling is the two famous examples. So let's do those. That's what I wanted to do today, were these two famous examples. And so let's do bound states first. WKB can be useful for finding bound state energies. And so here's the idea. Suppose V of x is equal to a well, a potential well, but it has a bumpy bottom. Bumpy bottom. A bumpy bottom well. And so here it is. Let's draw a picture of it. So suppose it looks like this. It has some bumpy bottom, some weird potential. Okay? So that's 0. And I'll just call this A. Okay? And this is V of x. So I just drew, so that's just some bizarre well that I just drew out of nowhere. Okay? And so now what I'm going to ask you is this. What is the energy of the bound states? All right. And so you've done this before. I mean, if it was a square well, you solve the differential equation and you match the boundary conditions, right? But now I give you this completely weird V of x, very complex. And this V of x is so complex that you have no idea how to solve the Schrodinger equation for this V of x. I mean, it's impossible, except for using a computer. You could numerically differentiate. You could numerically solve this problem via numerical techniques, but to solving it analytically is, there's no way you can do it. So you're sitting there going, well, how am I going to do this? And suppose that you don't have a computer to numerically solve the Schrodinger equation. So instead, what you do is you just say, let's use WKB. And with WKB, it becomes really pretty relatively easy. Still not completely trivial, but like 1,000 times easier. So what we do is we use the WKB solutions. And I say solutions because remember there's the plus minus. There's the plus and minus cases. So there's like those two solutions. So here's the WKB solution of the Schrodinger equation. WKB says don't numerically differentiate the Schrodinger equation. You don't need to do that. Instead, just make the assumption that the slowly varying thing is okay. And if that's true, then you can write down the WKB solution. You can say that the wave function inside of that bumpy well is equal to the positive one, A, over square root of k of x times e to the plus I 0 to x k of x prime dx prime, and then plus the negative solution, b over square root of k of x e to the negative I 0 to x k of x prime dx prime. Okay, you see that? So I'm just saying that that's the WKB solution that we derived, right? Here it is. We derived it using all that fancy math, and there it is, and now I'm using it. So I'm just saying I have these two components of the WKB solution, the +1 and the -1. I add them together in some arbitrary way, and that's got to be my wave function. That's the whole point of WKB. So you say, good, there it is. That's my wave function. And so now what do we do next? What do you think we're going to do to get the bound state energies? We got the wave function. So this is the hard part. This was like solving the differential equation. But now what do we do next to get the energies? Can you tell me? It's what you've done before when you've solved a similar problem. Well, it's a second order differential equation. So there were two solutions. We got them. There they are. And now that we got them, what do we do with them? How do we move forward? What's the next thing? You get the solutions of the equation, then what do you do? Well, if I gave you this problem, and I said, what are the solutions? You would solve the Schrodinger equation that says psi of x is equal to a sine kx plus b cosine kx. That's what you would get by solving the Schrodinger equation. And to get those energies, what would you do next? What would you do next? And you've done it a million times.
Wouldn't you plug in the boundary conditions?
Yeah, right. That's what you do. You plug in the boundary conditions. That's exactly right. So next comes boundary conditions. And so that's what we do with the WKB. It's the same thing. I just want you to see it's that same order of operations. Solve the differential equation, and that's what the WKB gives you. It gives you the differential equation solution, but then you still got to do the boundary conditions. So next we got to do the boundary conditions. But here's the thing. To do the boundary conditions for a bound state, then to do the boundary conditions for a bound solution, it tends to be simpler not to use the complex exponent, but instead of the complex exponent, what do we use instead? And it's right there staring at you on the page. So I want to convert the WKB solution to what? Can you guess?
Then cosines?
Exactly. So bound state problems, and you know this from last semester, are always easier when you use trig functions, easier with sine, cosine. But if you have traveling wave solutions are always easier with the e to the I kx, the plane waves. You guys remember that from last semester. So this psi e of x, so we'll convert it to another form, which you know that they're equivalent. It's 1 over square root of k of x to this. We'll do this a sine of 0 to x, k of x prime, dx prime, plus b cosine, integral from 0 to x, k of x prime, dx prime. Okay, so I'm just going from one form, just a simple transformation for convenience. And so now we plug this into the boundary conditions. So this is easier. And so let's plug it into the boundary conditions. And so let's do the first boundary condition is that the wave function at x equals 0 is equal to what?
0?
Yes. And so what does that say about the A and the B?
B equals 0.
Exactly. You got to have b equals 0 because that cosine messes you up. So this thing can't be 0 at 0 unless b equals 0. That's right. Good. And so now the second one is going to be psi at x equals a equals what?
0.
0.
Exactly. So 0. And so now at x equals a, it's going to be 1 over square root of k of a times a times sine of integral 0 to what? What's the top of my integral?
A.
Right. Because the phase winds from 0 to a. It's the little wheel is rolling along. And the phase is k of x prime, d of x prime. The b is gone. And so this whole thing is 0. But this whole thing can only be 0 when integral of 0 to a k of x prime dx prime equals what? Say it.
Is it n pi?
That's right. That's right. And so that's the constraint that you just derived. And so what you've just derived is that the integral from 0 to a of k, which is square root of 2m e minus v of x over h bar dx prime equals n pi. And so this is a constraint. This is a constraint on what variable? What, when you look at this thing, what's the only variable in here? Tell me.
The energy?
Yeah, exactly. So that's going to be, we'll call that E sub n, because you're going to get a different E for every different n. You see, they're connected. And so this is how you find, so you solve this to find the E sub n. So this is giving you, so it's taking this really hard second order differential equation and it's reducing it to this much simpler problem. It still might be hard, you know, because you got to you might have to still do some numerical work to even solve this integral. But solving integrals is easy, comparatively easy. Solving integrals is much easier than solving differential equations. Okay, and what I want you to also see is that physically, this is basically just doing something that you guys have done before. It's just, physically, it's what we're doing is we're just fitting an integral number of half wavelengths into the well. That's all this is. It's just fitting waves into the well. I want you to see that. We're just, the wavelength is changing of the waves as you go through the well, but what this formula is doing is just saying even though the wavelength is changing, you have to have an integral number of half wavelengths in your well. That's all that this equation is saying. So it's a sort of a very famous and sort of intuitive kind of result. Okay? And so this is what we get from Wkb. So this is a very beautiful and simple result. So, but, and you could do it, you could do it like for a square, you know, like if you had a, like suppose I have v equals 0 from 0 to a. You know, you're a situation that you know this one. So then what we see is we have 0 to a square root of 2me n over h bar dx prime is equal to n pi, and then we're going to get square root of 2me n over h bar times a equals n pi, and then you can solve that to get E sub n is equal to n squared pi squared h bar squared over 2m a squared. So this is This is the infinite square well. Infinite square well. So this is our favorite quantum mechanics problem. So you can see that I'm just seeing how the infinite square well fits into this formalism. But the point of this formalism is that it works for much more complex potentials than the infinite square well. So I want you to see that. But I'm not going to do any more examples of that. Okay, so now what we're going to do, so that's all I want to say about bound states. Now let's do tunneling. And this is actually the more famous problem. This is actually the more important one. Wkb is more importantly used in tunneling. And so what we want to do is we want to solve, we want to apply Wkb to tunneling. So here's the situation. Suppose you're given this. Suppose you're given this very weird potential well, where this has some very confusing V of x form, but then we have the energy is here. So suppose I shoot in a particle with that much energy at this well, and I want to know what's the probability to get through. The probability of transmission. That's my question. Okay, that's a very important question. What's the probability of transmission? Now, you guys have done this before, and so you already know, if you already kind of know what to do. If this region here is x1 and this region here is x2, then you know that I can label this region, region 1, and this region, region 2, and this region, region 3. And you know the form of the wave function. You know that in region 1, I have my incident wave function, looks like that, and I have my reflected wave function, looks like that. And what's the form? The incident wave function, what does it look like? What's the form of it?
E to the ikx.
That's right. And what's the form of the reflected wave function?
E to the minus ikx.
Yeah, r times e to the minus ikx. Yeah, exactly. And then here, then on this side, I have a wave function which is going in what direction on the right-hand side?
In the plus direction.
Yeah. And that form is going to be, what is it?
Is it t e to the ikx?
Exactly. That's exactly right. But here, now in this region though, it's confusing because normally you would have your exponentially dying solution and your exponentially growing solution, remember, from last semester? And then you would just match everything at the boundaries for the flat top, because you can solve the flat top, and you did that last semester. But now I didn't give you a nice flat top, I gave you a bumpy top. And so the bumpy top is so complex that you have no idea what to do. You have no idea what's going on inside. So what do you think we're going to do on the inside? Because to solve this equation, you know, we need to solve the differential equation, and then after you solve the differential equation, that's when you then match boundary conditions. The problem, though, when you have a bumpy potential is that you can't solve the differential equation. You don't know the solution. So what solution are we going to use on the inside? Tell me.
Can we still use the same solution, but the kappa
What solution?
is going
What solution?
the e to the I guess it was kappa x.
Well, those kappas were constants in the past.
Can we do that phase thingy that we were talking about instead on those?
Exactly, exactly. And that phase thingy is called what?
The Wkb approximation.
Exactly.
Okay.
Call it what it's called. It's called Wkb. That's right. We'll just use that very trivial phase approximation trick. And that's a trick for solving the differential equation. And that's what we'll do. It's not really the true solution, but it's an approximation to that solution. And that approximation is the WKB solution. So we'll use that. That's right. That's what we'll do. Okay, so let's do it. and then we'll match the boundary conditions. So let's do all that. And then the whole point is to find T, the probability of transmission, the transmission coefficient. Okay, so let's do it. So let's write it all down. So let's write out all the equations. So psi in region 1, psi of x, and I'm going to do it, this is how I'm going to do it for region 1. I'm going to call this, in the left-hand part, I'm going to call that solution e to the I k1x plus b e to the minus I k1x. Okay, where k1 is equal to square root of 2me over h bar. So does that make sense? So that's just the incident wave plus the reflected wave, where I used a and b instead of 1 and r, but it's okay, it's the same thing. And now in region 3 of x, I'm going to use this f as in Frank e to the I kx. That's the transmitted wave, where k, where I have the same, that's the same. Actually, let's not call this k1. Let's just call it k. So we don't need that one. Okay, so, and in the region 3, I have just f as in Frank equals e to the I kx. That's the transmitted wave.
Can I ask a quick question?
Yeah.
Would the transmitted wave, after having tunneled, have a different k to kind of, because I would assume like in between the energy is not the same, and to have like a continuity, it would have to like not have the same k as before?
No, that's not right, because the thing is that, remember, the wave function has a well-defined energy, and the energy is the same in all regions of space. And so the same energy on the left is the same as the energy on the right. That's really important. Do you see that? You see on the left, I'm going to do this. You see this thing right here? I'm drawing this vertical arrow. See that?
Yeah.
That is E minus V. And what is E minus V? Kinetic energy. That's the kinetic energy. So the kinetic energy on the left is E minus V. And now let's look on the right.
Oh, I think I'm confusing the energy with like probability or something like that.
Yeah.
Because it would have the same energy, but like the probability of finding it changes definitely, but not the energy.
Oh yeah, the probability changes all over the place. Right, the probability goes crazy, but the energy is the same. That's why I really want to make that clear. The kinetic energy is the same on the right and the left, and so the wiggliness, which is the K, is the same. But in the middle, it gets all crazy. Okay, so we're doing the easy parts for now, but the middle part is hard. So let's do the middle. Psi 2 of x. And so now we're going to use the WKB solutions. But now the WKB solutions are going to be a little tricky now. Let's go back to them. Where the heck is it? Yeah, so here's the WKB solution. See, I did it up here. You see it's here, right? I'm going to put a little star there. See that little star I just drew? Circle around it. So that's the WKB solutions. But notice that K is the square root. Where's K? Oh my God, K, where are you? There it is. Okay, here's K, where this little star is. K is the square root of E minus V of X. So K, now because I'm underneath the well, K becomes complex. So now the WKB solution will look a little different. It's going to look like, it's going to be C over square root of, I'm going to call it kappa of X times E to the minus integral x1 to x kappa of x prime dx prime plus d over square root of kappa of x e to the plus x1 to x kappa of x prime dx prime. See, that's the form of the solution inside of the region 2, and that's exactly the Wkb solution, but now it's not an exponent, it's not a complex exponent, it's a real exponent, right? Because of the nature of complex numbers. And notice that the starting point is well defined, x1, because it starts at x1 and then this phase winds to the location x. But now the phase is like, it's different. Now basically I have an imaginary phase, but that's okay. It's just complex numbers. You can handle it. Okay, so this is this form of the Wkb solution. And so now now what we have to do is find the transmission coefficient, T. And do you know what T is? Can you guess what T is in terms of these all these stuff that I've just defined? What is it that we're trying to find?
The probability of starting at 1 and going through into 3.
That's right. But in terms of all of these, coefficients, I have A and I have B, C, D, and F. What is T in terms of all those guys? In terms of A, B, C, D, E, F, what is it?
F magnitude of f squared divided by the magnitude of a squared.
That's exactly right. That's what we got to do. That's what we got to do now. And how are we going to find T? What are we going to do to find T? Same thing you did last semester. What are we going to do? By doing what? We have, yeah?
The boundary conditions?
Exactly. Because this is the solution to these are the solutions to the differential equation. And once you have the solutions to the differential equation, the next thing you do is you always do the boundary condition. So let's use the boundary conditions. And so but to do the boundary conditions, we're going to do some tricks. The tricks that we're going to do is we're going to assume large energy and not much reflection. And that is in keeping with the philosophy of Wkb, that the energy of the particle is very high. And if the energy is high, there's not much reflection. So what we're going to do is we're going to assume we're going to take out the parts that are due to reflection. Because look, in the solution number 1, what part is due to reflection? In solution number 1.
The b e to the negative ikx.
Exactly. So we're going to assume that b goes to 0. Now in solution number 2, what part is due to reflection? This is less obvious. Let's just take a look at region 2. In region 2, it's like I'm inside of the well, right? And if you guys remember how you have the exponentially dying solution and you have the exponentially growing solution, right? For the flat well, you remember that from last semester, right? And so the way to think about this is that this dying part is because as you move forward in the classically forbidden region, you go dying, you go down. But then you can hit that wall and reflect, and then you die a double death. Because once you reflect against that wall, you die some more. So if you go, you're dying, and then if you bounce and accumulated more complex phase, you die some more. And so this solution, which I'm giving a star, 2 stars, that solution is due to the reflection. That's how you should think of it. That's the exponentially, because remember how you always had the exponentially dying solution, exponentially growing inside under your well? And remember how you were always confused, why is there an exponentially growing solution? It kind of didn't make sense, but you just went with it, right? Well, that exponentially growing solution is really the reflected solution. It's the accumulated phase from the particle bouncing and dying some more as it comes back. So now back to the Wkb solution, which of these two solutions is due to reflection? The C or the D?
D.
That's right. That's the reflected one. Reflected solution. And so we're going to assume that D goes to what? Tell me. Because we're killing reflections. And so that means D must be what?
0.
That's right. Okay, and that makes everything a lot easier. So now let's match the wave functions at x1 and x2. Okay, and so what I have at x1, I have psi 1. See, this is x1. Let's remind you. See, here's x1 and here's x2. Okay, so those are the boundaries between region 1 and region 2. So I have psi 1 at x1 is equal to psi 2 at x1, right? And so that then gives me this incident wave e to the I kx1 is equal to now I got to do this one. I got to do this guy right here. And so it's going to be c over square root of kappa of x1 times e to the negative integral from x1 to x1 of kappa of x prime dx prime. So what does this integral equal? What is the integral from x1 to x1?
0.
Right. That's right. And so that's equal to c over square root of kappa of x1 times e to the 0 times 1. So that then tells me then that I have, so that's pretty useful. So that tells me then that A is equal to C over E, let's get this right. It's C over square root of kappa of x1 e to the negative I k x1. Okay, so we got A. That's pretty cool. But we need to get F, so let's do x2. And so from x2, we're going to do psi 2 at x2 is equal to psi 2, or psi 3, I mean, at x2. And so that's going to give me then c over square root of kappa x2. But now the exponent is going to be e to the negative, right? Because I'm still using this Wkb. It's x1 to x, but now it's going to be x1 to x2 of kappa of x prime dx prime. And that is going to equal the solution on the right-hand side, which is f e to the I k x2. Did that make sense? And so then that tells us then, now we can solve for f, and we see that f is equal to c over square root of kappa at x2 times e to the minus I k x2. We got f. So we got A, we got F. What are we going to do now to get T? T is equal to what? What do we do now?
Divide them?
Yeah, it's just F over A magnitude squared. So let's do that. So let's just divide those two things. So it's going to be magnitude squared. I'm going to put the F on top, and that's going to be C e to the minus I k x2 e to the negative x1 to x2 kappa of x prime dx prime square root of, oh, and then let's get rid of that. And then I have my divided by square root of kappa at x2. Okay, but now I got to divide that by a, and so for a on the bottom, I'm going to have e to the negative I k x1 times square root, oops, and then the square root is going to be on top because I'm dividing it. So on top it's going to be square root of kappa x1 magnitude squared. Okay, now there's a couple of things to notice here. First, I want you to look at square root of kappa x1 over square root of kappa x2. And that, now kappa, what the heck is kappa? Did we define kappa? I'm sorry, I didn't even write down what kappa is. I mean, kappa is going to be equal to square root of 2m v of x minus e, because it's underneath potential, and that's kappa. But what is kappa at x1 and x2? So kappa at x1 is equal to the square root of 2m e minus v of x1. Oops, let's get the signs right. V of x1 minus e. But what is the definition of the turning point, or this point where these cross? See, at x1, the energy hits right here. So at what special thing is, what is the relationship between the V and the E at x1 and x2? The potential and the energy at x1 and x2. What can we say about them? We're almost done. I just want to finish this last little bit.
They are equal at the turning points.
Yes, these are the turning points. Turning points. E equals V. And so what does that mean then? What do the kappas equal? What do they equal? I got this minus this. V and E are equal. And so what is kappa equal?
0.
That's right. And so this thing is a 0 over 0. Now, this is actually slightly tricky if you want to like delve into all the mathematical nuances of it. But you know me, I don't. I don't want to do that. I'm not a theorist. I'm not so excited about all those mathematical nuances. I'm just going to do the cheap and simple thing, which is to say that 0 over 0 is equal to what? Tell me.
1.
1.
Yes. But I will tell you that I am sweeping stuff under the rug. There is some trickery, there is some complexity that happens at the turning points in the Wkb approximation. But I have been using Wkb for 30 years, and I have never had to worry about that trickery in 30 years. So I'm just going to ignore it because it sort of doesn't, it's never been important to me. So you see that these two guys are going to cancel. And when I do the amplitude squared, then these two guys are going to turn into what? What's going to happen to these two factors?
They go to 1.
They're going to go to 1. That's exactly right. And so in the end, we get this. We get that T Oh, and something else, there was another C down here. I'm sorry. Because F has a C in it and A has a C in it. So there's a C on the top and the bottom. So the C's cancel. And you get that the transmission coefficient is equal to basically just this integral squared. And so that means it's going to be e to the negative 2 integral from x1 to x2 kappa of x prime dx prime, where kappa of x is equal to square root of 2m v of x minus e over h bar. And that is a very famous relationship. That is the famous Wkb relationship for tunneling. The transmission the Wkb tunneling transmission coefficient. It's very famous and it's very useful because it's very simple. That's the result that we just derived. And it's just so simple and beautiful. It's just, if I have a potential and I want to know the probability to tunnel through it, I just have to integrate, do this little simple integral. That's all I do. And so that's what, we just have to do now the integral under that potential. Okay, so that's a good place to end. I'm sorry for going over. Bye-bye.
Thank you.
Okay, bye-bye.
Thanks.